Thank you very much for the introduction. I'd like to thank the organizers for the invitation and the opportunity to speak. This work is an application of Craig's formula for the block probabilities, and it's also somewhat of an interpretation through the Burger's equation of this formula a little bit. And and this is joint work also, before I forget, with Pramit Gosal and Ethan Sell. Pramit from Columbia, he's somewhere here in the audience. And Ethan, he's a graduate student at Virginia. And I'm going to warn you that this talk is going to be somewhat interactive, so watch out. I'm going to ask questions. So the outline, I'll introduce the model and the result really quick. It's pretty easy to state, so it's nice to just put out there. And then I'll talk about the background. I'll try to spend most of the time on the background, as I think it kind of really motivates the result and the answer. And then we'll end with the proof or the sketch of the proof. And really, to see this interpretation of the block probabilities, we need a certain symmetry due to integrability of the ASEP with multiple species. So, and the proof is, it's a cute proof. It's not too difficult to give this the proof of the statement, but it really relies on this symmetry due to integrability. And it turns out that this symmetry is generalizes for more sophisticated interacting particle systems. And so I like to highlight that part of the proof. So we'll start with the ASEP. Craig already introduced it, so we can go through it pretty quickly. We're going to have the, oh no, where's the, here we go, laser. So again, we're going to have asymmetric jumping particles, probability P to the right and probability Q to the left. And opposite to Craig's talk, just to confuse us all a little bit, particles are going to be jumping to the right with higher probability, so the drift in this talk is to the opposite way. And if you're confused, just kind of turn your head the other way, and everything will be fine. And we're going to have the simple jumps. The S stands for simple jumps, so each time it's going to be jumping by one site at a time. And then there's the exclusion rule, which is denoted by the red lines. And it's a Markov process, continuous time Markov process. So the evolution of the particles is dictated by independent exponential clocks for each particle. And this is the usual colorblind ASEP model. The model that we're interested in is going to be a model with second class particles. And in this model, there's two different types of particles. First class particle, which I color blue, and I label it by 1. This is going to have higher hierarchy than the second class particle denoted by 2, meaning that if a first class particle wants to jump to a position that's occupied by 2 particle, then it's going to swap positions with 1 and 2. So if this particle 1 wants to jump here, these 2 particles are going to swap, but not the other way around. When you have the number 2 particle, you're trying to make a jump to a position occupied by 1, it's not going to be able to do it. So the one way to think about it is that 1 sees 2 particle as a whole. It doesn't detect it. And in this, for the initial conditions that we're going to be discussing in this problem, we're actually going to take step initial conditions, and we're going to have an arbitrary length of number 2 particles at the beginning. So this is what we're interested in. And in particular, we're interested in the distribution of the last second class particle in the configuration. And we're going to look at the distribution as time increases. And using the block probabilities and this symmetric result due to integrability, that's how we're going to be able to prove it. And this project actually started last summer during a summer research program where we were just doing calculations, simulations, and in particular, we just started simulating second-class particles. I was just wandering around. I had no idea what I was doing, but I was suggested that I look at the second-class particles, and I started with the simplest case that I could think about. It's the second-class particle at the very front, and I plotted an empirical CDF, and in here, this was up to time 1,000 and 10,000 trials, and in here, this is the moment for name the degree of that polynomial. So what is this degree? That's just a straight line. So that's degree 1. So the first one is pretty easy, pretty straightforward. I struggle a bit to figure it out. I was thrown off by the deviations near the boundaries. And then the next one is going to be if we start with 2 second-class particles, and we're trying to look at the distribution of the last second-class particle. And in here, I wanted it to be the same as the first one, as the previous case, but it doesn't look the same. There's a slight difference. And here, it's slightly less time, 500, 10,000 trials still. And then the question was, name that CDF. And so the first thing that I tried, I had no idea what it was, but my first idea was to actually try to just figure out the degree of this thing or what it is. But since it's an empirical CDF, it's not continuous, it just kind of jumps. And actually, through some numerical derivatives, when you take the derivative of this guy, you see that it's degree what? This is a polynomial. Degree 2, yeah. So you look at the second position, then you have a degree 2, you look at the first position, you have a degree 1. So what's the conjecture now? So if you have L particles, it's going to be degree L. And we tried to do the simulations for degree 3, and we could detect that it was a degree 3 polynomial, and it was a pretty close fit. And then once we get to degree 4 and degree 5, they all just look the same. You can't really tell them apart numerically. So at that point, we tried to just prove the statement. And the initial conjecture was to prove that this distribution was a degree L polynomial. And that was just what we wanted to do. And it turns out that we can actually say what the distribution in large time is going to be. And in this setup, we're going to have L plus 1 particles, since we start at 0. And this x star sub L is going to be the location of this particle, the one at the very end. And then when we scale by t and take the limit as t goes to infinity, we see that the CDF, or 1 minus the CDF, is actually given by this distribution where we have the same asymmetry parameter that's written right here, except with p minus q, because we're going in the opposite direction. And it's actually when we were in this stage, when we had the simulations, this is when I started talking to people, asking people if they knew what was going on, and eventually I landed on Promit. He was familiar with the subject, and he knew the results for ASEP, and it turns out that there's a history about this problem that he was well aware, and he started pointing me out in the right direction, and then we started discussing more. So at this point, I like to discuss some of the history, and right now I'm just gonna let this CDF be and just state it as it is. And so the plan now is to go through the background so that we can have a better interpretation of what or why or how we should expect that result, why it's natural. So in here, the connection that I'm alluding to is going to be to the Burger's equation. And the thing is that if we look at the ASEP in the hydrodynamic limit, we're going to have that the density function for the process is going to obey a Burger's equation. And in this hydrodynamic limit, we scale things to epsilon, send them equal to 0, and we get this Burger's equation. And this is going to be satisfied by the density. This is the expected value, which, since it's an indicator function, is just going to be the probability. It's going to be the density of our particle. So really, it's going to describe the profile, the density profile of our particles as it evolves. And this is just, I guess, it's somewhat technical. I'm comfortable with the heuristics. I should have had a reference, but let's just assume that this is true, and we have this interpretation of our density function. And the thing about the Burger's equation is that the solutions travel in, they have traveling wave solutions, so that you can actually pick characteristic lines for the solutions, so that you have characteristic lines so that the solution of the Burger's equation is constant along that characteristic line. And in particular, you can actually compute explicitly, you can show explicitly that the characteristic line is going to be given by a straight line where the velocity, the direction, the slope of the line is given by the position, by the initial configuration, and then it's just going to follow that straight line. And it depends on just the initial location, and the amplitude really just depends on the function initially. And the thing that we are going to look at is this type of step initial conditions. Depending on your initial conditions, that you can have characteristic lines that intersect each other or behave in a certain scenario. So we're going to look right now at what happens with different initial profiles, how the characteristic lines behave. And in this type of behavior, this is when we're going to see the application of the second-class particles, because it's going to tell us something about the characteristic lines. So the first scenario that we're considering is the shock scenario, where we start the initial density with some density lambda and some density rho. And here, lambda is going to be greater than rho. And we can, by the formula given before, we can give the characteristic lines. So they all depend on the initial value at time 0, and then they just become straight lines. And due to the fact that it's the discontinuity, we have this shock formation. So along these lines where the lines intersect, this is what's called a shock. And if you're a surfer, a surf enthusiast, wave enthusiast, this is really just the wave breaking. And this is essentially what happens, is that your solution at this point becomes multi-valued. And you can talk about the Burger's equation in this scenario through weak solutions. And in the interpretation for ASEP, the application here is that what we're going to do is that we're going to go back to the pre-scaling limit, and we're going to add Bernoulli step conditions with probability rho to the left of the particles. So probability rho at each side, there's going to be a probability p of having rho of having a particle there. And then on the right, actually I have them backwards. That's typo. So turn your head the other way. And then lambda on the right is going to be the density of the particle. So with probability p on each side independent, there's going to be a particle. And what we're going to do is we want to look at what happens in the shock. So we're going to actually place a second-class particle at the middle where the shock first is formed. So right in the center of the profile, wherever the first intersection happens, that's where we put a second-class particle. And the result from Ferrari in 1991 is that if you look at ASEP with shock initial conditions, and we put the particle right at the middle of the shock, then when you evolve the system and you center it by the position of the second class particle, what you see in the hydrodynamic limit is that the profile is going to stay the same as the starting profile, meaning that it's going to follow the shock. So what happens here is that it's that the second class particle, as you evolve ASEP under shock initial condition, keeps track of where the shock is. So it's going to be following the shock. So it's going to be the surfer on the wave.
So do you want a 1 or 2 on that?
1, because in here this is centered at the second class particle, and then we're looking away from the second class particle. And then moreover, we have that the speed of the second class particle converges to this speed of the characteristic line.
This Ferrari is Pablo.
Yes, Pablo Ferrari. Thank you very much. I get confused myself. So this is one scenario, and then the next scenario is the rarefaction fan. Whenever you have that there's more, the density of the particles is higher on the left than on the right. And in the previous shock initial conditions, maybe I should describe why we should expect I should have explained why we expect the left to move faster than the right. But in this case, it's the same logic. In this case, we're going to expect particles to be moving slower here than in this region. And the thing is that they have the same asymmetry in ASEP. They're both sides have this P minus Q asymmetry, this drift to the right. But when you're in here on the left side, since there's more particles, there's going to be more blocking, and that's going to slow the particles down. Whereas in here, there's going to be less density, so there's going to be less opportunity, less blocks, and so you're going to be able to move faster. So in here, you're going to expect that particles move faster in this region, and particles on this side are going to move slower. And it's going to be due to a blocking. And on the other scenario, we saw that whenever you have it the other way around, that causes a shock. And in this case, this causes what's called a rarefaction fan. And it's in here we look at the characteristic lines for the Burger's equation, and we see that they're just going in opposite directions. And here in the middle at 0, you actually have a family. You don't have a unique characteristic line, you actually have a bunch, and this is what's called rarefaction fan. There's different ways to do the characteristic lines, and this is what's called the entropy solution. And this is, we just compute everything with the simple formula we introduced before. And in here, what ends up happening, we do the same thing where we now go back to the pre-scaling limit, and we set up our ASEP so that the hydrodynamic limit is the same as we're interested before, and we put a second class particle right in the middle. And we want to see what happens. And the thing is, we want to know, in the previous case, when we put it in the shock, we saw that it followed the shock. And in this case, we want to see what it's going to do. And this is a result by Ferrari, Kipnis, 95, and Ferrari Goncalves, sorry, for the Gonzalez, and Martin, 2009. I believe, if I remember correctly, that in 95, they proved it in distribution, and then in 2009, it was in almost surely convergence. But it's saying that the speed of the second class particle when you put it in the rarefaction fan is not going to be, so if we go back, it's not going to be, it's going to choose one of these blue lines uniformly. So when you start the motion of the second class particle, what's going to end up happening is it's going to pick almost instantaneously. It's going to pick one of these directions. It's going to pick one of these directions uniformly, almost instantaneously, and then throughout the rest of its path, it's going to follow that single specific characteristic line. So at the beginning, we have. Question?
I have a question. In the previous case, the shock speed, does it depend upon P and Q, or is it always the entropy shock speed?
This one? This is the speed. So I'm not entirely sure the difference, the subtlety in your question, but hopefully this helps.
The speed does depend upon P and Q.
Yeah.
Thanks.
Yeah, thank you. And also on the density of the left and the right. And so now when you're in rarefaction, you actually are choosing uniformly. And this is the result, and it's going to be in this uniformly in this compact interval. And so actually, sorry, I guess I misquoted this statement. The almost sure convergence doesn't happen here in the ASEP. It's just in distribution, this convergence of the speed. Whereas for TASEP, one can actually show that the speed converges almost surely. And there's further generalizations of these ideas where you can set up arbitrary rarefaction initial data where it's not, you look at scenarios where it's not just two independent Bernoullis, but rather you just want that the left side of the density on the left side is going to be greater than the right side. And so you just look at these two quantities, and under this general arbitrary initial conditions that are in the rarefaction regime, then you again, in the work of Cator and Pimentel, you put a second class particle in the middle and you try to track it. And under fairly arbitrary initial conditions, they just need this to satisfy this condition. Then you can actually, they give an explicit formula for the speed. It's going to converge to a random variable. And they give a specific construction, which is made up of a random walk whose steps are built out of some exponential random variables that they construct explicitly. And in interest of just being concrete, I consider this special case where now I have no particles on the right-hand side, and on the left, I'm going to have all class 1 particles, except that L to the left, L sites away from the origin, I'm going to put my second class particle. And it's kind of the same scenario that I put up in the initial problem, where I just look at L distance away from the origin and I try to see the distribution. And in fact, in the case of TASEP, they're able to recover a similar distribution where gamma is set equal to 1. So from this point of view, we already expect the gamma inverse in here. So this result was already shown in TASEP, and this result, again, is in distribution. And moreover, there's also this idea of tracking the second class particle is also important for this TASEP speed process. That was introduced in 2011 by Amir, Engel, and Balco. And what they do, instead of just looking at two types of particles, they're going to introduce a particle that's actually, that all particles are colored differently, and in here I actually change notation slightly, and now in here the smaller particles have the hierarchy that this one can overtake this one, and this one can overtake this one, but each particle is colored differently in this case. And this is the, and in our work, in our result, we actually use the ideas from this, this work, and we actually have to introduce this model to actually get the symmetry result that's needed for our proof to relate the second class particle to block probabilities. In particular, there's going to be two ways to look at the configuration of the ASEP speed process, or this ASEP, multi-species ASEP. And one way is to record the color of the particle in location n at time t. This is going to be eta, which is the similar type of thing that we looked at before. And the other way to keep track of the configuration is going to be the location of particle color n at time t. And in here, when we're going to be looking at the configuration, at the initial conditions where the particles are all just in increasing order. And just in here, we actually, one of the results from their paper in 2011 was that they can actually using the results of ASEP with almost sure convergence in their speed, they can actually do the convergence of all the speeds simultaneously, and they all converge to a uniform random variable from -1 to 1, and they all converge almost surely, and they converge to this family of random variables. And this family of random variables, this is what's called the ASEP speed process. And for this definition, you really need the convergence of the almost sure convergence of the speed of the second class particle. And once you have this convergence, once you have this theorem that's due to the almost sure convergence, you can actually say a lot of interesting things about the ASEP speed process. And in particular, one thing that you can keep track of is convoys of particles, meaning particles that kind of just stay at the same speed and travel together. And you can actually show that there's a non-zero probability that two adjacent particles will just stay together and always travel in the same direction with the same speed. And you can actually keep track of the interaction between particles. And the thing, morally speaking, what's happening is that you're distinguishing all particles from each other, and you can actually keep track of all the interaction. So it gives you a more refined understanding of the ASEP process. And what one would like to do is actually try to do this for ASEP, where you can actually keep track of all the colors and actually get more information about their interactions. But it really depends on this convergence in almost sure convergence of speed. And right now, the only results are in distribution. But in their work in 2011, they show that once you have this almost sure convergence, given that assumption, then you can do the same results that you have for ASEP, and you can have a lot of information. So this idea of keeping track of the second class particle also brings a wealth of information to the ASEP process. So that's also another interest of trying to keep track of the second class particle. So now I'm gonna discuss the proofs, do a sketch of how I'm going to, so let's recall the statement. And so again, I'm trying to keep track of this last second class particle. So now that with some of this background, now we can intuitively see what is going on here. And what's happening here is that when we had one particle in a rarefaction regime, then the one particle would choose uniformly from all the possible characteristic lines, and then it would go in that direction. So the CDF for that particle would be given by a uniform distribution. So now when we have two particles, for instance, again, it's going to have the same thing is going to happen. They're both going to essentially choose a uniformly a characteristic line, and they're going to follow that direction. But due to the exclusion rule, the second particle has to pick the minimum of those two characteristic lines. So in here, what you get in that scenario then is that the last particle is going to be the minimum of L plus one uniform distributions. So from that point of view, that it's choosing characteristic lines from the rarefaction fan, and it's the last one, then it should choose the minimum according to a uniform distribution. And so this is the statement that we saw through the simulations, and this is going to be the strategy of the proof. What we're going to do is we're going to take a coupling between second-class ASEP, the one that we introduced, and the ASEP, the multicolor ASEP that I introduced with the TASEP with general jumping parameters. And then with that coupling, we're going to then use the symmetry argument between these two different types of ways to tell the configuration of multicolor ASEP, and which uses an integrability result. This symmetry is really due to Yang-Baxter's integrability. And then at the end, once we translate the event of the second-class particle into blocks, we can use the result that Craig provided for us, and we are lucky that we don't have to do any of those asymptotic analysis. So that's going to be the strategy of proof. And so this is going to be our coupling. And I have about 5 minutes. So at the top of this figures, we have the ASEP process that we're interested in. And at the bottom, we have the multicolor ASEP, which would extend on both sides. And what we're going to do is we're going to couple each pair of particle connected by a blue line is going to share an exponential clock. So these two processes are going to evolve simultaneously, but there's going to be, and then they might evolve differently due to the exclusion rules. And here we see, for instance, that if this clock is activated, in the bottom model, we're going to have that this -1 will jump, but this one won't. And whenever that happens, what we're going to do is that if in an event of this type of event, we're going to switch the coupling, and we're going to couple this second-class particle with this other particle. And again, we're interested in this on the last second-class particle. And then again, if given the first move, if again we have another move of the first-class particle in here, then if both can move, then we're going to move them together. And what's going to end up happening is that in the rest of the evolution of both processes, whatever happens in the rest, this second-class particle is going to be stuck with the zero-class particle. So now we can just really think about it, think about these two models at the same time, and really what's going to happen is that whenever we evolve our model with second-class particle, it's going to evolve the same as the minimum of these 3 particles. So in this case, we have 3 particles here, and we look at the first 3 particles here, and the evolution of this particle is going to be the minimum between these particles. And that's how we're going to evolve, and now when we want to know the probability of this, we're just looking at the minimum of these 3 particles. And it's essentially this idea of just, in this case, this 3 particles will choose uniformly on one of the rarefaction lines, and then we're just going to take the minimum. So this now we need a symmetry result that's due to the integrability. And this result was first stated in the ASEP speed process paper, and later on it was improved to a more general setting by Borodin-Wheeler. And in Borodin-Wheeler, that's where we saw the statement where that was more relevant to us. And essentially what's saying is that the distribution of the configuration, if we keep track of the colors, and if we keep the track of the configuration by the colors, or if we keep track of the configuration through the position of the colors, then these 2 configurations are going to have the same distribution. So whenever we speak about this process, which is what we're doing in here, we're keeping track of the location of these 3 particles. Instead, we can keep track of what color is in each location. And so what ends up happening is that when we're looking at the minimum, we're looking at this probability, and then we can turn it into a probability of what's the color at these sites. And then by translation invariance, we can just shift everything up. And then this probability is just telling you that the colors are greater than 0 at each of these locations. And then by turning the multicolor process colorblind, this is essentially telling us that there's a gap of length L in this probability is equal to a gap of length L, which is the probability that Craig computed. And so now we turned it into a probability of finding a gap in the colorblind result that starts at location S. And this integrability, this symmetry result is really due to this integrability identity. You can do the evolution of ASEP through random transpositions. So you can define configuration at time t by random permutations, where if the configuration is in decreasing order, this tau n is going to switch these 2 configurations, is going to do it with probability 1. And if they're in increasing order, then with probability p is going to switch them, and with probability 1 minus p, it's not going to switch them. So you write your generator for ASEP as a sequence of random transpositions, and in the ASEP speed process, they actually show that this random operators actually satisfies these relations, and this last relation is the Yang-Baxter equation, is the intertwining relation, the braid relation, and this is really what powers the result between the 2. And essentially, when you're looking at these 2 types of configurations, you're actually looking at them as if they were permutations of the integers. And the result, it boils down to this result for their random operators. And essentially what it's saying is that if you apply random operators in a specific order, then you do it in the opposite, then that's going to give you the inverse permutation with the same probability. So in here, I apply pi 1, then pi 0, and I get these configurations. Then I do it in the opposite order, pi 0, pi 1, pi 1, and then I look at the inverse, and they're going to have the same distribution. So what you can do is it allows you to evolve, to look at the 2 opposite things with different evolutions, and it allows you to translate from one configuration to another. And this is essentially the integrability result. And now what we need to do is we need to compute the block probabilities, but opposite to what Craig did, he computes, or not opposite, but not exactly the same. He computes the blocks starting at particle m, and we want blocks starting at position s. And whenever we use his whenever we use this formula, we actually have to, since we're interested in location ST, we have to use the formula for this formula actually for the location M is going to be given by sigma t. And by solving for sigma, we can actually see that sigma is going to be 1 minus gamma inverse S over 2 squared. And since we just want the particle to start at S, then we just sum over all the possible particles starting, blocks starting from there, and it turns into an integral, and we integrate the probability density function, which gives us 1, and then we recover the minimum of L plus 1 uniform distributions. And then the last thing is that this symmetry result of looking at the two types of configuration, this is actually works in the color 6 vertex model, and it's a recent result from Borodin-Wheeler in 2018, where the color blind result and the color result are the same. Thank you for your attention.